Welcome to the Shack of M1 GEO. Recently on Twitter, I'd noticed a few people talking about how they were correlating the UK mains frequency that comes out of the power outlets here in the UK with things that were happening on the network, such as power stations going offline and load shedding and similar things during quite a large storm. So this is some ideas about how to go about measuring the mains frequency, how I've seen it done as a hobbyist a few times, and a few other ways, or another way that I thought of doing it and how I kind of tinkered about with that. But it's really relevant to anybody that's looking to measure low frequencies quite accurately. So it's just a few slides with some ideas. Let's first look at the current way this is done, or one of the ways it's done as a hobbyist, and that's by using an Arduino, a Nano, or a Uno, or something similar, and using the interrupt pin, usually D2, which is interrupt 0 on the processor, and using that with a length of wire attached to that pin and just leaving it floating so that it picks up noise essentially. And if that wire is placed near a mains power cable, it will pick up the 50 Hz mains hum, and then that's used to interrupt the CPU in an interrupt routine, and that then counts frequency and measures it against the CPU clock. And there's a link at the bottom and also in the comments where there's some example code that does this. It works reasonably well, but there are some problems with it. So some of those problems are that the antennas will pick up stray signals. So when I played around with this code initially, I noticed that it would quite often pick up double the mains frequency, and it was reporting values of around 100 Hz rather than the 50 Hz that I was expecting here in the UK. Another issue is that it picks up strong switching transients from switch mode power supplies. So if you've got any power supplies sitting on the bench or in your shack, some of those were being picked up, especially the poorer quality ones with less filtering inside them. On the main side, it was sort of every now and again jumping to a few kilohertz and tens of kilohertz, picking up switching frequencies in some of those. And I also did once see it trying to measure a VLF or LF band frequency on 472 kilohertz. Started trying to measure that as well, so that caused some issues. So lowish frequency ham radio transmissions cause issues as well. Aside from things that it picks up stray signals, you've also got the issue that the CPU resonator isn't particularly stable or accurate. Cheap Arduinos that are commonly found on places like AliExpress and eBay, they're not using the best quartz crystals and having those trimmed to perfect frequencies. They're just random resonators that are very cheap and are good enough for most applications, but not really ideal as a timing reference for this kind of project. So that leaves us with a sort of wish list of things that we would need. So what do I need to do a better job? I wanted firstly to be connected directly to the mains, and there's a little caveat with that not directly, but through isolation transformers and making it a safe voltage to work with. But I didn't want to be just wrapping some wire around a cable and picking up stray signals from the mains. I wanted to be directly connected to it. I wanted to low pass the signal so that I would remove any of the switching transients, and in the end I did that with a very simple low pass filter RC network. And I also wanted an accurate timing reference, so I didn't want to rely on the 16 megahertz resonator that was on the board with the processor. What I arrived at was something looking a bit like a frequency counter, as you might expect, but working sort of slightly differently, slightly in reverse. So if we sort of look through what's going on here, there's a 10 megahertz reference, which is a known good signal. We're assuming for now it's a perfect 10 megahertz. Comes into some kind of signal conditioning and arrives at an AND gate. And then the mains frequency is latched and filtered, which gives us a pulse every time the mains goes through a zero crossing. And so at the output of this AND gate, well, it's not exactly an AND gate, but you get essentially the number of times the 10 megahertz perfect signal cycle during the one cycle of the mains, and it gives you a ratio. And then you can see that the mains frequency that you're trying to measure is equal to your reference frequency divided by whatever this counter counts. And so every time this 10 megahertz goes up and down during the mains period, it counts that value, and then on the next cycle it latches that, the CPU can read it and display the result of this calculation. And so, for example, if the count value is 200,203, if you divide the 10 megahertz reference by that value, you can see it gives us a value of roughly 49.95 hertz. If the count value is higher, the higher the count value is, then the lower the frequency is, because that implies that the mains frequency cycle was longer and we were able to count more of the 10 megahertz cycles. More of those made it through in the period, so the period must have been longer than we expected. So obviously you can look at this and say, okay, 10 megahertz divided by 200,000 is exactly 50 hertz. So that's the frequency we're aiming for. The count value rather we're aiming for is 200,000. Anything above that means the frequency is low, and anything below that value means the frequency is slightly higher. So the CPU then reads the counter and is able to compute this, and it also sends the value to the PC as well. So what parts did I use? I used a Symmetricom UCCM-P GPSDO commercial 10 megahertz frequency reference, because I know that that's a good stable frequency reference. There's no need to worry about it. I can just connect to it, and I know that I've got as good as I can afford to have 10 megahertz reference in this shack. I used a transformer coupled output from the mains. Actually comes from a wall clock, which is main synchronous. So this ended up being a 6-volt AC sine wave from the mains. Goes through a small low pass filter, and then onto a board with an opto-isolator connection. This opto-isolated signal then goes into a lattice MAC X02 FPGA, and then an Arduino is able to read the count values from the FPGA after that's been gated and measured, and just display the result on a Hitachi 16x2 LCD. So what that looked like in the shack is a bit of a mess. I use quite often pieces of laser cut acrylic, this red sheet here and this black bit, to do different projects, and these are things that have been used before. You can see here there's a GPS module that's unused in this project, but I've used it for previous things before. You can see here the mains frequency that we're reading, so 49.9 something megahertz on the little LCD, and the mains frequency is coming in here on this grey cable. There's the opto isolator and a little just an RC network low pass filter here with some diodes to protect the opto isolator. Underneath here is under this board is an Arduino Uno. You can see the USB connection just here, which goes back to the PC for logging. The 10 megahertz reference comes in over here. It's on 2 pins, comes in via a small SMA to 0.1 inch header. And then you have the big FPGA here. Some interfacing into the Arduino between the two. And the USB connection also provides power. So that's what it looks like. So how did it work? Pretty well. The LCD shows the frequency directly in hertz, as you just saw, and I've seen frequencies from around 49.8 to 50.1, 50.2 hertz, and some of these graphs here show kind of what that looked like over the course of 20 hours. So you can see the frequency drifts quite a bit. These glitches here, and you can see some more of them here and whatnot else. These glitches here are, I believe, because I'm using a solar hybrid inverter, and so as the inverter switches between charging and discharging the battery, and exporting solar and stuff like that, I think there's some kind of phase discontinuity or something strange, slightly strange happens, and that causes a bit of a glitch. So I don't think these are real, but you can see the kind of trend. Obviously, this data comes from the USB logging, which allows for better capturing, but it generates quite a bit of data. So this is just a raw plot. It's also possible to kind of take this and filter it, but working with these large files is quite difficult. Here I've just plotted kind of the first section of raw data, and that's shown in grey. You can see the noise, kind of noisy measurements there, with sort of every few cycles. But moving average filter, you can see in black, shows the trend much more clearly. And you can see here the frequencies, a little bit more kind of confined. At the moment, this generates quite a lot of data because you have kind of a measurement for every cycle or two, so it's making quite a lot of data. But that doesn't need to be the case. So what could you improve, or what could I improve if I was to do this again? I'd probably do some averaging on the Arduino, so that would make it so that I could send less data back to the PC, maybe just an update once per second or something like that. Because as I said, the huge ASCII files that it generates, and it's generating about 30 megabytes of data an hour, that becomes quite difficult to handle in text files, especially when you have to like compute them or turn that into a graph. It takes whatever spreadsheet tool you're using some time to get all that sorted, and uses lots of memory and can crash on. Certainly crashes my low-end Shack PC. I would probably replace the Arduino with an ESP8266 or an ESP32. That way you could upload things to ThingSpeak, so the data could be uploaded to ThingSpeak. That would allow you to do a lot of this measurement in the cloud, a lot of the analysis in the cloud, run a moving average. You can get a nice looking graph that can be, can easily be viewed and also shared. And it's done automatically via Wi-Fi, so you could just make a little box that purrs away doing this if you're interested in it. One other option is, which is probably worth pursuing, is to look at replacing the FPGA with an 18-bit or more counter. 18 bits the minimum you would need to count to 200,000 thereabouts. So, and some CPUs allow you to use both an external gate and an input. So you could put both the 10 megahertz in and use the 50 hertz signal as a gate signal to trigger the count to be latched and reset a new one. So if you're interested, there's some links both to the original Arduino code that kind of prompted some of this, and also to my GitHub page with this project on it. And the frequency counter project GitHub page has both the FPGA Verilog inside and the Arduino sketch, so you can play around with that. You can also use it with a 1 pulse per second from a GPS and make quite a good frequency counter. And with that FPGA, you're able to count well over 500 megahertz with a 1 pulse per second from the GPS, and it works pretty well. And that was the reason for the other GPS on the dev board originally. Hope you found that useful and or interesting, or maybe perhaps it prompted you to have a think about something or start your own project. But hopefully you found it useful, and thank you very much for watching along.